In this video, we're going to look more closely at the quantum numbers that correspond and describe the angular momentum. We're going to have to rely in a sophisticated way on the concept of analogies. An analogy, a comparison in which an idea or a thing is compared to another thing that is quite different from it. When we're looking at the concept of quantum numbers, we have, I think, three distinct eras we want to be aware of. What the classical physics would describe are early descriptions of Bohr, and then finally the more full-blown quantum mechanics. We find that when we go from the classic to the early quantum, it's really a combination or a melding of some quantum aspects but retaining quite a few of the classical ideas. When we extend that to quantum mechanics, it becomes quite different. No longer do we have distinct orbits. We're describing atomic orbitals. We're relying on a description involving probability. What I'm trying to say is that when we go from this classic to a quantum mechanic description, we really need to attend to the fact that we're making an analogy. We're not looking at something that is literally the same. So even though we might use language that is classical in nature, we have to keep in mind that we're simply making an analogy. Looking a little bit more closely at the ideas of analogies. I like this one, as we often encounter analogies in writing, in reading the works of authors. Analogies as in writing may be describing either identical relationships or shared abstractions. So when we're taking this into the discussion of quantum mechanics, we might have a particular property that we can measure. And there's a classical explanation for that property. That same property could be measured if we're thinking about it in terms of quantum mechanics. The identical relationship here is, what's identical is the property itself. The property that we measure is something that, whether we think about it classically, think about it in terms of quantum mechanics, the property can be thought of as being identical in both respects. But what's abstract is the explanation. When we go from the explanation of the property, we're going to see that our minds might be using language, might be understanding and using language that has a classical description, but that's definitely in the domain here of we're comparing two things that are technically unrelated to each other. This is not an easy task for us to try to do, but we definitely see examples. So the Knight textbook, which I like a lot on this topic, there's just a few examples when he's discussing orbital angular momentum. Notice the language. The ground state of hydrogen with L equals 0 has no angular momentum. A classical particle cannot orbit unless it has angular momentum. But apparently a quantum particle does not have this requirement. There's a discussion of what a particular property is, how to think about it classically, but then pointing out that that's not the same when we think about it quantum mechanically. We have a particular property, but it's dissimilar in terms of the explanation. Same thing after having the idea of shells and orbits. In quantum mechanics, nothing's really orbiting. Within our analogy, it's going to mimic certain aspects of classical orbits for the electron's motion, and it provides a useful analogy, but it's saying, once again, we are not looking at literally the same thing. The explanation is different. We're thinking about an explanation perhaps classically, but we don't want to say that that is what's actually taking place quantum mechanically. Perhaps most telling, we see that when we're looking at electron spin. The electron is most assuredly not a classical particle. Characteristics of spin is as if the electron is spinning. We're having this notion that the property, the electron has spin, but the classical explanation is not appropriate. So within this discussion here, this is what we're really tasked with. We're considering quantum numbers And we have to ask, how are quantum numbers then supporting an analogy? So we have, different quantum numbers. If we have a description for our wave function, we find that quantum numbers n, l, and m sub l are shown there. As Atkins describes when we're looking at then our overall wave function, is having both a radial and an angular component. There's particular quantum numbers describing that. So here he's showing for a 2px orbital, we would have a radial component that depends on n and l. Combining that with an angular component, L and m sub l, that allows us to have a radial wave function and then the overall atomic orbital. So notice within here we had 3 different quantum numbers that were being used, n, l, and m sub l. So when he goes on to say when the Schrodinger equation is solved for the 3-dimensional atom, it turns out that we have 3 quantum numbers to label each wave function. That's what that point is illustrating, n, l, and m sub l. Beginning with the n, pointing out that that's one that we would have encountered earlier within our Bohr model. Goes on to say that this name reflects the fact that as n increases, the region of greatest probability density is like a nearly hollow shell of increasing radius. There's a description there for the energy. Students' comments and their understanding in this area. I found this one was useful. A student commented, "This is a great way to imagine probability density for anyone who may be confused by it. And it can connect the values of the density to a familiar topic of the shell of the electron." That's definitely what the author was intending. What this student is describing is, okay, they had a sense of the Bohr model or the de Broglie model, and they were able to extend that then to the Schrodinger model. They were able to begin with a classical description, see how it then was applying for the Bohr or de Broglie model, and then extend their analogy to the Schrodinger model. I find that this is something, out of all the quantum numbers, this is the easiest one to do that. To go from a classical description to see how Bohr is using it and then extend it to quantum mechanics. Now, when we do this, let's keep in mind, once again, we're still drawing an analogy here. This language, as n increases, the region of greatest probability increases like a nearly hollow shell. So that's not literally what's taking place. If we want to describe where the electron's found, we have our radial probability distribution functions for different atomic orbitals. Notice these are not describing a nearly hollow shell. We have other internal features for that. So if we're looking at, for a 3s, we have a radial probability distribution function. Where the electron is found, this is not a nearly hollow shell. We have a lot of other internal features to that. I find that when students seek to interpret this kind of depiction right here, many times they view this as being a combination of a 1s and a 2s and a 3s orbital. That's not what this is describing. This is the entire 3s orbital with all of these different features. So in some ways, I find this image right here being more useful because it shows what the 1s, the 2s, and the 3s all correspond to. When it's given just in isolation, many times students divide it up that way. What they seem to be doing is they're saying, okay, I'll buy into a description of a solar system model that we see akin to Bohr here, where we have a 1s region, or excuse me, an n equals 1, n equals 2, n equals 3 region. So when they then take it to a radial probability, they seem to just superimpose all of those. That's not what we have within our quantum mechanical description. Moving from the principal quantum number to L and m sub l, if we look at the relationships, a few questions come to mind. So both L and m sub l, they seem related to the orbital angular momentum because they both have L after all. And if they're both related to the orbital angular momentum, how are shape and orientation then related to each other and to the orbital angular momentum? We can ask, are these ideas also included within the Bohr model? And Why is magnetic part of the description? So all of these are questions that I've seen students raise before. So let's begin to investigate that. And in our investigation, let's keep in mind these two parts. We have a classical description that then features of which show up within Bohr's model that then get extended to quantum mechanics, and that we're then drawing an analogy from a classical description to our quantum mechanical one. And that particular analogy, again, it might be similar in terms of the property that we're talking about, but the explanation is really describing dissimilar things. That's what we're going to try to keep in our head. So for orbital angular momentum, I need to refresh my own classical description. So what was my understanding here back in high school? So for orbital angular momentum, we consider that as, let's first of all say it's going in a circle. We've got a particle going in a circle. The orbital angular momentum depends on the inertia and the angular velocity. So I remember back from high school this example that the angular momentum is conserved. If you got an ice skater spinning around, drawing the arms in, their angular velocity increases. To represent the magnitude of the angular momentum, the convention here is that we have an arrow perpendicular to the plane in which it's rotating. And the length is proportional to the magnitude of the momentum. So in classical mechanics, what happens? Well, notice the magnitude there. The orbital angular momentum, it could have any value. It can't be zero if the particle is orbiting, but beyond that, it could have any value at all. How does that then show up within the Bohr model or the de Broglie model? We have the same rings after all. I think the Hyperphysics website does a good job of discussing the angular momentum within either the Bohr or the de Broglie model. So we have our de Broglie wavelength. We have the condition then for a standing wave. By simply putting those together, what we find is that the angular momentum, L, is quantized. If you remember our symbolism, h over 2 pi, that's what h bar corresponds to. So we see that as the principal quantum number n increases, the angular momentum also increases. It's quantized. So in contrast to the classical one, what would be that magnitude? Well, it could be h bar. It could be 2h bar. It's got to be in some increment involving our principal quantum number n. So is orbital angular momentum included in the Bohr or the de Broglie models? Absolutely. It's directly related to n for the circular orbit, so we didn't need another quantum number, but it's absolutely an important quantized feature. This is something that we don't usually mention when we're bringing up the Bohr model, but it was absolutely a feature within that description. And it's definitely pointing again to the strangeness of what happens when things are quantized. If the orbital angular momentum is quantized, let's say you were spinning a ball around, you could change the rotation, you could change the velocity, but it would have to take place in discrete steps. It couldn't continuously change. So you can imagine it perhaps in our head, but that's not the macroscopic world that we have. But that is now what it means when we begin to have another aspect be quantized. So classically then we could have a nucleus, an electron, and a circular orbit around it. This wasn't the end of this particular model. It began to be modified. So in the Bohr-Sommerfeld model, there's a description of how then the simplest Bohr picture then was adjusted. Why was it adjusted? Well, as was pointed out, the line spectrum for the hydrogen atom, as we know, is an important feature that supports Bohr's description. But if they look closely at it, it wasn't completely right. Okay, there was the aspects of lines being split, and then also aspects of, even though the Bohr model gave us information about frequencies, it didn't tell us anything about, let's say, the intensity of the different peaks. If you look within the PhET-Sim, the models of the hydrogen atom, If you let the one for the Bohr model run and you let the actual experiment run, you find that there are some differences. Bohr does a great job of matching up the frequencies, but every time you run it, you see that the intensities do not match up. I let these both run, so the red line was about the same intensity, but you notice that then these are not identical. So the scientists of the era were aware of that particular shortcoming. So how do they begin to modify it? So Bohr's analysis of the hydrogen spectrum was not completely satisfactory. Bohr has really the simplest description. It only has one quantum number. It's putting electrons in these circular orbits that are all in the same plane. If we want to begin to expand our model a little bit and perhaps increase its explanatory power, we're not necessarily restricted to simply circular orbits. What if we now begin to consider elliptical orbits? So instead of having simply be in the xy plane in a circle, let's make it an ellipse. So here's some descriptions within the Bohr-Sommerfeld model where it now introduces another quantum number. We have our principal quantum number n, and we now have one describing the orbital angular momentum. So we see here the next way to expand the model is to go from simply circular orbits to also now include elliptical ones. Now, the elliptical ones, they don't necessarily have to be restricted to be in the xy plane. What if our ellipse was off of that particular plane? So we're going to use this convention here with the z-axis up, and here we have a tilting away from the xy plane. So we can talk about the magnitude of the angular momentum perpendicular to the xy, and we can also think about it back relative to the z. Classically, what do we have? Well, the L value, it could have any value. We would have a corresponding L sub z value, the projection along the z-axis, and we could simultaneously measure any of the values along the x, y, or z. In Bohr's model, notice how we've changed it. We've quantized the description for the angular momentum, our L term right here. And I would say that the L and the L sub z have to be the same because within our Bohr model, we had our rotation only in the xy plane. We were tilting off of it. Quantum mechanics, somewhat different picture. We again have the orbital angular momentum quantized, but it's a square root of L times L plus 1 times h bar. We know the different allowed values for L, 0, 1, 2, 3, etc. So if we put these in the description, we find that these would be the allowed values for the orbital angular momentum. L equals 0 for the quantum number L, then the overall orbital angular momentum 0. We have it quantized in these different specific values. One other thing within this description here, turns out that the z component is also quantized. It must have one of the values where L sub z equals m times h bar, where m is an integer between negative L and positive L. Does this sound familiar? Well, that's what the m sub L value describes. Both L and m sub L seem related to each other and related to orbital angular momentum. Both have L? Absolutely. So what they're really describing would be what is the property for the orbital angular momentum that would be perpendicular to the orbit, and what would be the projection along the z. Shape, orientation, and orbital angular momentum are related to each other in this way. And that's what these quantum numbers are actually describing. The L is describing the orbital angular momentum. The m sub L is then that orientation of the rotation relative to the xyz. So our description then of quantized orbital angular momentum, we see figures like this. So there's a lot going on here. So let's step through what this is telling us. So first of all, in each case, we have a projection that corresponds to the L value. This would be the allowed values for that. And then we have where it then matches up back to the z-axis. So this one right here would be as if this was the particle in this orbit. We have a projection perpendicular to that. And we see that the projection then along the z would be 0. These values that we have correspond to these classic orbits that are tilted with respect to the xy plane. It could be right in the xy plane or tilted at different angles. And then these would be the corresponding magnitude and then the projection back to the z. So the way this fits together, when the orbital angular momentum is measured along the z, in this case right here, I see 5 different values. 1, 2, 3, 4, 5. What would be the corresponding m sub L values? It's these terms right here. We could have -2, -1, 0, +1, +2. Those are the different values that correspond to the projection along the z-axis. What type of atomic orbitals are we talking about? This would be the representation if we're looking at d orbitals. How about the L value? For d orbital, that's the square root of 6 times h bar. The thing that I take away here is that for a d orbital, we're talking about an actual specific angular momentum value. There's actual units right here. It's not just some abstraction. It's corresponding to an actual measured value. What would be the angular momentum for the electron and hydrogen in the ground state? Well, that's a 1s atomic orbital. L equals 0. For the quantum number, if we plug 0 into our expression right here, we'd see that it has no angular momentum. That's back to Knight's description that a classical particle cannot orbit unless it has angular momentum. But apparently a quantum particle does not have this requirement. It comes back to this discussion of analogy. This depiction right here, these would be the values that would correspond to classical orbits for a particle that's rotating with respect to the xy plane. What we're saying, though, is that an electron is not a classical particle. These would correspond and explain the property that we can measure, but that's not the same explanation that we need to have when we're thinking about it for a quantum mechanical particle. We have allowed values. Those are what we could potentially measure. These values can correspond to then classical orbits that are tilted with various respects to the xy plane. But these are not the literal trajectories for our electron. Electrons, after all, are not moving in classical orbits. Electrons will have the same measured angular momentum values as if they were these classical orbits. But this is really driving home the fact that the classical explanation might be how we think about it in our head, but that is not the same explanation that applies then quantum mechanically. We have a classical description for the property. We can draw an analogy to something that is actually quite different, which is the quantum mechanical description. So, to wrap up right here, we saw that we had 3 quantum numbers involving the Schrodinger equation, N, L, and M sub L. Both L and M sub L seem related to orbital angular momentum. Absolutely, they're describing the magnitude of it or the projection then along a particular axis. That's how the shape, orientation, and the orbital angular momentum are all related. Are these ideas included in the Bohr model? They initially are. We see within the Bohr model there is quantized orbital angular momentum, but it had a different condition. It was then certainly explicitly then included in the Bohr-Sommerfeld model, where we had two quantum numbers, the principal quantum number and also L. We haven't yet got, though, to the language on the magnetic. Why is M sub L called the magnetic quantum number? And for that matter, how do we measure something like the orbital angular momentum? Those are things that we will explore in a subsequent video.